compression techniques, audio compression techniques, right? In which, according to the syllabus, the first topic, I'll directly go to the topic, that is DPCM, all right? Differential, correct, pulse code modulation. So in short format, this is DPCM, right? So DPCM is actually, right, a coding technique that is used, which does not reduce the size of or the number of samples that needs to be stored. Okay, I will not be able to see the compression happening in terms of the size. Like, okay, I'm not able to convert a 10 KB file into, say, 4 KB. No, that's not happening. But, right, the compression happens because the size of the location needed to store a specific sample is reduced. Okay, like, let me assume that I have a 8-bit data, right? Let me assume that if I send the data as it is without the DPCM technique, right? If I want to save, right, 1 pixel of an image, let me assume I need 8 bits to store one pixel value, all right? If you apply the DPCM, right, this is, say, 8 bits without DPCM. Okay, right? So there is a pixel value, right? 1 pixel value, that is f of x comma y. This is true even for the audio sample. Okay, I have an audio sample. That sample uses, say, 8 bits to store. 8-bit audio, we have the most common one. 10-bit audio is there now, which is more clear. Okay, so the 8-bit or 10-bit means that that is the amount of space needed to represent one sample of your data. Okay, if it is image, it will be a pixel. If it is a audio, it is a single sample of the audio. All right, let me assume that instead of using this, I apply the DPCM modulation. I'll apply. Right, now if I try to represent the same thing, you require less space. So only the number of space required to store a single sample got reduced. You see, maybe 4 bits. Okay, so that is 4 bits, right? Now you see that we never altered the number of f of xy. The number of samples we never reduced. Okay, it's still same. You had 100 samples, or if the image size is, say, 10 into 10, it will remain 10 into 10. I'm not compressing that. I'm not reducing the image to a smaller size. Okay, but you see, you saved the amount of space required to save that particular data, right? Okay, so that's the idea. Okay, 4 bits. Maybe this is just an example with the DPC. That is our fundamental idea. Now, in order to make things more clear, right, make this concept more clear, I will start with one part of this DPCM, which is the PCM. Okay, so it is actually, right, it may look like, okay, I have to do something with the PCM to get the DPCM, right? That's actually, that is not true, right? It's slightly different than the PCM, but let me explain what is a PCM first. Okay, very quickly I'll go through the PCM. Right, PCM stands for, you convert an analog signal into a discrete signal, and every sample in the discrete signal gets coded. Okay, for example, let's go with the example here. Say this is analog signal. I'll draw the analog signal first. Maybe this is what is the analog signal I'm considering. So this is the time. This is sorry, this is amplitude. Maybe that is x of t. All right, so let me say I sample this, right? This is, you perform what is called as a sampling. Now, what is the care that you need to take when you sample out any signal? What is that? Do you remember anything from any other subject you studied already? Right, you have to satisfy the Nyquist rate. Otherwise, what happens if you don't satisfy? What is the problem that you face? No, no. Huh, huh. If you don't sell, because of some reason, Nyquist stated that, huh, okay, you're close enough. The word we are looking for is not distortion, it is aliasing. Okay, it's aliasing, right? So aliasing in the sense you are not able to reconstruct, right? Ice, right? You will not be able to reconstruct the signal. Right, correct, right. So that's the problem. That's because of what the problem you face is aliasing. There will be aliasing when you don't satisfy. Okay. No, no issue. That's okay. That's okay. So it's fine. Absolutely fine. Okay, no issues. Fine. So you might have studied this in maybe digital communication or somewhere if you had that subject, right? Communication system, right? So fine. Okay. Now let me assume that this particular signal has the x of t has a frequency that is fm, f max. Okay, highest frequency in that signal is f max. So according to the Nyquist rate, whenever you sample, you should use a sampling frequency, right? That should be equal to or greater than 2 times the f max, correct? This is the condition for PCM. I'm quickly going through the whole concept of PCM without any equations. Okay, I'll quickly go through that because that helps us in understanding the DPCM. Okay, right. So let me assume that I sample at these points. Okay, whatever red marks you see, those are the discrete points on the curve, correct? Which is a result of sampling. Okay, again, it depends, right? You may be able to represent the signal completely or you lose the information. Everything is fine. We studied already in the uh, in what is called as the communication system, right? So I don't want to talk about that, right? Fine. So these are the different samples. So now the axis is not time, right? This will be the n ts value, n times ts. Okay, ts is 1 by fs. All right, so I'll also write that here. So ts is equal to 1 divided by fs. Okay, so you see this will be 0. This is 1 into ts. So this will be ts. This is 2 times sampling duration and so on. This will go. Already, this is fine. Anyway, we don't have any issue with it. Now, what happens in PCM is this. You get a value here. Maybe this is, say, 1.2 volts. Okay, assume. Right. Also, I need to make a change in the representation over here. This is no more x of t, but this is x of discrete nts. All right, okay. So 1.2 I get. Maybe the next value what we receive here, the representation should be something like maybe if maybe I'll write just 1.5 volts. So you have the same sample there. Maybe you have another sample here, right? So that is maybe 0.9 volts. Let me assume. Okay, so these values you get, correct? Right? This value has to be converted into a code. Like you can choose like how many bits you want. What is the number of bits required? Say for that actually basically is decided by the total number of values, vertically discrete values you have. If you have simply 8 values possible starting from 0, you need 3 bits, correct? Because everything is binary, 000 001 dot 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 up to 111. Correct, in the sense if this is 0, this is the first sample, the second, third, fourth, fifth, sixth, seventh and eighth, let's assume. Okay, we have 8 samples vertically. 8 different discrete values are possible, means you can give the code like 000 001 and so on. Are you okay? So in other words, I don't want to bring even the binary here because that's not our concept. What we want to see is how what is DPCM, how it is different from PCM. So PCM means every value on the y-axis, vertical axis, gets coded into some binary values. Okay, so that is what is PCM. So let me write that. Okay, so let me write just a word PCM here. This is what happens in PCM. Very simple. Okay, fine. So PCM part is over. I'll move directly to the DPCM part. Now, so anyway, what I do, I'll copy the same this thing once again, because I can draw the DPCM from this. Okay. So here I'll write the DPCM. Right. I still go with the same process of sampling. Okay. There will be sampling. This is the first thing. And right, again, this will be x of nts only. It's still the discrete version. Okay. No problem with the sampling of that. So I have nts, and I'm going to have x of nts itself here. But you see, while doing the sampling, I don't stick to the Nyquist rate. I go beyond the Nyquist rate here. Okay, so the fs is pretty much greater than 2 times f max. Okay, now, so obvious one, there will be many questions in this particular part. So the first question will be, when you increase this, you have more and more samples coming out. First thing, right? That actually, right, you need higher data rate for a communication to happen, right? That's the first thing. Okay, let's assume that, let's overcome that problem now itself, thinking that, okay, I have a very sophisticated communication device which can send the chunks of data in a very quick fashion, something like very fast hardware. Okay, say I have a very like in the gigahertz range, something working in the gigahertz range. I have FPGA with me. Okay, much faster than the processors. Like let's remove that problem here itself. Okay, so no issue with the, no issue if you have more number of samples. Okay, fine. But because of this, right, maybe I'll assume that I increase the sampling rate by 10 times possible. Okay, but these were the two samples which I had earlier. Okay, maybe it may not be 10 times. I'll make it 5 times. Okay, I need to get 5 more samples between them. 1, 2, 3. Okay, let me see, totally 5 samples I got. Okay, right, compare that. I'll whatever I'm marking with double these things. So this is actually the original sample. Okay, now I have few more samples marked over there. They are the additional samples I'm getting. Okay, like that. So I think I had another one here, and maybe another one somewhere here. This is what I had earlier. Now I am going to get more samples in this. That's all. Okay, I increased the sampling rate. Right, that is the first difference we have to remember when I consider the PCM and the DPCM. Okay, that's fine. Now, in addition to that, what happens when I consider what exactly the DPCM is going to do, I will understand now. Why I actually increase the number of samples, there is a specific reason, right? There is no way I can reduce the size required to store the data unless and until you increase this, right? You do the increase this, right? I'll come to that point now. So let me mark few points here just for the reference. Okay, so fine. Now I think I need to do, I just want to enlarge this, okay, so that I can draw properly what exactly I'm trying to do here. Okay, now you see, consider, if at all you try to do the calculate the values now. So I think, what was the value I wrote earlier? I think this was something like 1.2, I guess, maybe, right? I think this was 1.2. Okay, and this value, I think I wrote that as 1.5. Correct. Okay, now you see I have few more points, so I'll just try to draw those values. Right. So again, let's stick to the PCM. Then I'll come back to the DPCM. How do we get the DPCM part? Okay, I need to divide this into, say, 3 equal parts, right? 1 point how much? There is point 0.3. I need to divide that by 1, 2, 3, 4. So maybe this is 1.27. Okay, 1 point maybe 35. Okay, 1.42, let's say. Okay. Anyway, this is going to come in 3 or 4 decimal places. I truncated them. Let's say. Is it okay? Fine. Now you see what we try to do in case of the DPCM is that, right? Remember PCM, I used to send them as it is. In the sense, I used to convert them into a into the, say, if you are using 8-bit, you convert them into 8-bit numbers and you send as it is, no change. Okay. But now you see, instead of sending 8-bit numbers, now I will tell you what we are going to do here, right? Between every sample, you have what is called as a difference. Calculate the difference because it is a differential, right? What you do, you calculate their differences. So here you get 0.07. Okay. This could be 0.08, right? Again, this can be 0.07 and the next sample will be 0.0, I think 8. Possible? Now you see the number of bits required to store or to send this data is very less compared to this data. Okay, sending 1.5, 1.42, 1.35 is difficult in the sense the number of bits required is very much larger. Number of bits required is more compared to sending these differences. Right. Again, why you increase the sample? Now the obvious question, I'll reduce the size. Now there is another obvious question that is coming up. Why don't you do that with the PCM itself, right? You can do that with the PCM, calculate the difference and send this and that, right? Right. So that question is there because there already you have a less number of samples. You don't have to burden your communication system. First thing, and the second thing is that yes, there also you can do the same. Correct. Now you see there is the if you try to reconstruct by just using the differences, I have a problem. See the reconstructed signal will be something like this, right? You miss it. Okay, you miss the actual part, right? So whenever you take the samples and you want to send something like the errors, this is what is I call as error. Okay, whenever you want to send these error, in the sense it's like the difference between the successive samples. Yes, right. Whenever you want to do that, we want to make sure that this difference is very small. As you reduce this, the maximum value that you might get between the samples, you call it as highly correlated. There is a lot of correlation between, sorry, I'll change the color because everything looks red for us. Okay, the correlation that exists between this sample and this sample, the two neighboring samples on your DPCM, okay, is right. That correlation is it's very high compared to the correlation between any samples you find on the PCM, right? That's why we had to increase the sorry. That's why we had to increase what is called as sorry. Just let me come back. Ah, okay, that's why we had to increase the sampling rate. So that's the reason why we increase the sampling rate overall. Okay, right. So now it should be clear that what we are trying to sell. Right. So let me write the concept related to this so that, right, it you can even answer explain part, explain the differential pulse code modulation, or there can be a question saying that what are the differences, right? So you will be able to answer that like this. Okay, so the first thing we consider that I had a analog signal and I sampled at Nyquist rate, which resulted in the PCM. Okay, so I'll not go with that. I'll directly go to the DPCM part. I'll start with the DPCM part. So I'll write here. This is the DPCM. So just remember these two graphs so that you can compare the points. But anyway, I'm going to write few points over here. Right. Let me assume that if we sample the analog signal, any analog signal you consider, and you sample the signal at a rate what rate? Much higher. Okay, at a rate which is much higher than the Nyquist rate. Right. We observed one thing, that is the correlation between the neighboring samples or successive samples increases. Correct. So Nyquist rate, I can directly write. Okay, the neighboring samples will be highly correlated. Correlation increases. Now, what do you mean by this highly correlated data? The difference between them is very less. Correct? See, if you remember, maybe in DSP or somewhere we have studied the concept of correlation. You might have studied autocorrelation, cross correlation, many types of correlation. Correct? Right. What is the ultimate goal of doing that whole operation of correlation? To find the similarities. Correct? Yeah, you try to find similarities between two different signals, it is cross correlation, right? So irrespective of what type of correlation you do, you are trying to find the similarities between the two signals that you are trying to correlate. Okay, now look at the results of correlation. If the similarity, if you find the similarities between the two signals, or if they are highly correlated, the answer of correlation is a high number, bigger number. Higher value comes out after the operation is performed. Once you finish the correlation, if the two signals are very similar in the sense, when you take a difference, the difference is very small. Correct? Okay, now you see the same concept I'm applying here. Since I'm saying they are highly correlated because of sampling them at a higher rate, the difference between their amplitudes are very small. Okay, so I can easily write this because of our understandings of what is called as a correlation, right? This implies there exists very minute difference between magnitudes of those successive samples. Is it okay? Right. Now you see. So then what we perform? We try to measure their values, right? Like you can see here, right? We try to measure the values over here, right? Measure in the sense again you do a truncation over there, right? Whatever is allowed to be written, you will write that. Like, see, in this case I am writing only 2 bits, 2 digits after the decimal, but actual value could be, see, I simply wrote 1.2, but maybe that value is 1.1993. Okay, so you see, you did a truncation, right? So what do you call that kind of operation along y-axis? Horizontal axis, if you discretize, it is called as a sampling. What do you do? What do you call the, it's not exactly sampling, so I cannot use the word sampling, but just to make you understand, I can definitely use that. So what do you do if you sample your y-axis? There is no 1.993, it is 1.2. There is no 1.2663, there is 1.27, like that. If you discretize your y-axis, there is a specific word in communication. So I think you have studied, that's why I'm asking again. In communication system, what is the next step of sampling? If you recall the process of conversion of analog into digital, analog signal to a proper digital signal, first you do the sampling. But what is after that? After sampling, something comes up. Just recall. No, not modulation. No, not modulation. Modulation is basically, modulation is conversion of the signal, which is most of the time baseband, okay, into band pass. Okay, so you try to convert the signal into some format which can be transmitted. Okay, so that is modulation. So here it's not modulation. You can see I'm not doing any modulation here, right? What is this? The writing of the numbers like fixed numbers on the y-axis. Do you remember? Yes, perfect. Right. So what you do here is the quantization. So what are the advantages and disadvantages? Just two questions because it is useful in our next discussion. So while I write the word, you just try to recall what is the advantage, what is the one advantage, one disadvantage. Okay, just try to recall. I'll write the word here. So this is the quantization. All right. Okay. Are you able to recall? Advantage just now we discussed, right? I don't need to write each and every number that might come because of sampling. You may have 1.2233. Next number will be 1.3386, right? All numbers, the representation becomes very difficult. Okay. So you fix, right? Okay. My number will be either 1.2 or 1.27. In the middle, whatever comes, I'll truncate. Okay, either I'll make it 1.27 or I'll make it as 1.27 or 1.2 depending on, right, what is suitable for me. Again, you have a quantizers, mid riser, mid trade, many things we study, correct? Right. So okay, according to some rule I do the quantization. That's the first thing. What could be the problem? No, that comes later. Now, from whatever we discussed, you try to answer. So I got 1.23. Sorry, what was that? Okay, I got 1.233. But right, using some quantization technique, I converted this into 1.2. What you did actually, you introduce. Are you introducing error? Right? Right, you purposefully you are introducing error. Your actual value is 1.233, but you write it as this, so there is an error of 0.033. This is a problem. You see this problem in our DPCM, right? For sure. Okay, I will show you in the decoding process. We get the error, we cannot do anything with that, we have to tolerate that. Okay, so that's the problem. That's why I brought the two terms here. One is the quantization, one advantage, one disadvantage. Okay, right. Anyway, we don't have to write that, you just have to remember, that's all. Okay, so we understood that successive samples are highly correlated, because of which we have the fixed amount of what you call uh, so okay, they are highly correlated, and the if you take a difference, it is very small difference between the amplitudes. Correct? Okay, let's proceed further. The next point I want to write here is that what we performed what is called as a quantization, right? If you try to encode every samples, right, as it is, like I am trying to encode 1.27, 1.2, uh, uh, 1.35, like that, all those values, if you try to uh, encode, and if you try to maybe you want to save, or maybe you want to transmit, whatever, okay, I it's obvious that, right, I don't need that data to be sent, because 1.2 only you send 0.07, it's understood that my next value is 1.27, correct? If it is lesser, send a difference in the negative value. That's all, right? I want to come down from 1.2, means send minus 0.07. That's all, correct? So that's the idea here. So I'll write one point here. If all these samples are quantized. So this has to be done because that's a fundamental step of the conversion of an analog into digital. Okay. So it has to be, if all the samples are quantized, right? Immediately after quantization, you perform encoding, okay? And encoded, then we have, you see, you that info, all these information is not required, correct? That means we have the redundancy, uh, redundancy in redundancy in the information to be sent or to be processed, whatever, right? That's fine. I'll stop here. So in the information, we have redundancy. So what we do, we go for the DPCM. So in the DPCM technique, right, to reduce the redundancy in the whole information, right, only the difference between the successive samples will be used. Okay, we use the, yes, difference between successive samples, successive samples, right? That means if you want to store only the difference. Okay, you want to transmit only the difference, right? So now let us look at this this process, right? This diagram may be required for you to when you answer a question. Okay, so what I do, I'll try to write the y-axis here, only the y-axis, not required with the x-axis. Okay, so I'll give a, this again, this looks like a comparison for you. You can use the same set of diagrams for the comparison between PCM and DPCM. Okay, so in case of the PCM, I'll write on the left side. What happens in the DPCM, will write on the right side. Okay, now, okay, first let me write a PCM. So in the PCM, the y-axis should be very large, because you have to write each and every possible value your signal can take. Are you okay? Like maybe, right? Maybe let's say this is 0, right? I might have to go till all the way till 5 volts to represent a signal, right? Whose sample value could be, okay, I'll write, I don't want to draw the sample values here. Let me assume that I have two sample values, such as one sample is say 4 volts and one more sample will be say 3 volts, right? What do you send, right? What you are going to send is the number 4 and number 3 directly, right? So that means in case of PCM, I require more number of levels, correct? You see, you may divide your sample, like, okay, this is, say, you may say that this is 0.5. That's fine, that's not an issue is that you have to go all the way till the highest point. In the sense, if it is 10 volt signal, you see, you have to go all the way from 0 to 10. Okay, so I'll say in PCM you require more levels, right? More levels actually means that more number of bits, correct? For representation. Okay, bits per level. That's my point. Right. Again, yeah, actually, if you recall the concepts of PCM, I can write an equation also here. How to calculate the number of levels. That I don't want to write, because anyway, I'm not. We are not interested in that part. We already studied that in the communication. Okay, so now I'll come to the DPCM. You see, DPCM. Consider. Let's go back. You see, what is the maximum error I find here in this diagram? Maybe it's very small. I'll try to enlarge. So look at the error. What is the error? What are the errors that you read here? The black colored values written, point 0. So what could be the maximum value you need on the y-axis? What do you need? What is the maximum value? You see, you don't have to go till even 1 here, right? Right? Okay, so you are understanding that, right? So anyway, I'm sending the difference, right? Maybe, right, if I'm trying to send the difference, let's say assume you just have to divide, maybe this is 0, this could be just 0.1, right? In the middle, whatever comes, you divide, right? So 0.2468 and zero point 0.1, right? So 0.02, 0.04, 0.06, zero point 0.08. That's all you need. How many levels you have? Lesser levels. Lesser levels imply what? Lesser number of bits, right? Lesser bits per sample, or lesser. Okay, I'll write like level, because that's what makes more sense here. Okay, lesser bits per level. Number is small, that's all, right? So you actually have saved a lot when it comes to the uh, what you call the size of each information bit, that each information that you want to save, correct? So I'll write. So as I can see, levels increase here. That means even the number of bits increase in this case. Okay, whereas in case of DPCM, you have lesser levels, levels reduced. This implies number of bits reduced, again not by a small factor, by a very huge factor. Okay, where is 0 to 10 and where is 0 to 0 0.1, right? So just see that. Yes. So again, this is just an example. When you go to a practical case, you have, just imagine, I sample a signal in gigahertz range. Let's assume my sampling frequency is gigahertz, right? That means you get 10 to the 9 samples in 1 second. So difference between each sample will be, right, of the order 10 to the minus 4, 10 to the minus 6, something like that. That's the difference. That's the gap between the levels, right? So you see a lot of compression happens over. Okay. Right. Okay. So this is the whole concept you need to understand to relate it to the DPCM. That's the theory part. Okay. Let's move to the block diagram. This is also equally important. So the second possible question here, first is either just explain or uh, do a comparison. Do a comparison between the two. That will be your first question. Okay. So we answer that. We'll move further. Okay. So the second part is the DPCM encoder. So next question could be draw the DPCM encoder or and the decoder, encoder and decoder. That will be a question that comes normally together. So let's assume that I have the analog signal, right? That comes from here. Okay, I'll save some space by moving this. Okay, we have an analog signal that is taken as input. Okay, so the first part that we give the signal is to what is called as a sampler. Anyway, I know that I get the samples first. Right. Now, this sample should, from this, I should subtract the previous sample, correct? Is it okay? How do you get the error? How do you get the error? These values, whatever I wrote in the black color, that is obtained by what? No, not quantization will give the red values like 1.2, 1.27. So after the quantization, right, I have to subtract, correct? I have to subtract. So what I do, I'll use say the quantizer over here. Let me assume that this is a quantizer. Okay, fine. Now let me add a block here which performs that subtraction. So this comes here. This is my quantizer. So quantizers, I want to make sure that before this I do the subtraction. So this is positive, this is a negative, right? Whatever comes down. But how do I get that part? That should be right one sample previous to this, correct? Right, right. So what we do, we use a block over here. Let's put a block here. Right. So this is a, we have a prediction filter. Again, we will see that we get the input to the prediction filter from here. Okay, before that, I need to do another part because this output will go to, so this is error. Okay, output of the quantizer is what is error, error quantized. Okay, quantized error. Okay, let me write that. So I have, say this is x of t. Output of sampler will be x of n ts. Okay, uh, whatever comes from below will be the predicted value. Okay, so we do denote that as x cap of NTS. What is that? That is your predicted value. What will be the past value you predict? You don't have to use a memory. It will do the prediction automatically. Okay. So from there, it comes to this. At the same time, we have a connection from here to this. Okay. Right. Now this simply gets, it is added here and it will come to this. So you see the x cap of NTS is a prediction value. Prediction value plus, okay, I'll write an error here. This is E of NTS. No, this is the error. This is the error between present value and the past value. That I will quantize to get the EQ of NTS. Okay, now what you do, you encode this error and transmit, correct? Or you say, according to our, so I have to use what is called as an encoder here. Right. So the output of this itself is the DPCM. All right. So what we do, okay, we'll quickly write the equations required. All right. So the same equations we will be using when we solve the problems. Okay. So the error signal, how do you calculate error? It is E of NTS. That is equal to, look at the equation. I have X of NTS. I am subtracting the X cap of NTS. Is it okay? Just check. So this is equal, this is E of NTS, left hand side, equal to this minus this. Okay, so that's the first equation which we have to use and we have to remember. Okay, so next part, the next equation I'm going to write is the quantized error signal. Okay, so that is okay, just try to recall. Anyway, I'm not able to show you that inside this because I understood one point when I asked a question about what is the disadvantage of a quantizer. So the answer we got there was it introduces an error, correct? So I'll write something like this. Okay, this is quantized error. So that is output EQ of NTS should be equal to, you see, input to that is E of NTS, isn't it? But how do you get EQ? XQ of NTS. Uh, where is that XQ coming from? Okay, okay. This part you are calling, I think this. Okay, so yeah, right. That is the quantization error, correct? So you remember, right? Input is an error. Error is something like 0.2335, right? This gets converted into 0.2 means you actually introduce an error here. That is this, correct? You try to convert this with you subtracted 0.0335. So that is QE here, right? Are you okay? Right. Okay. So that means I'll just write here just as a notation. This is the quantization error. Now I will calculate what is the input that comes to the prediction filter. Input to the prediction filter. So denoted by, as you told, this is XQ, correct? XQ of NTS. So as we can see in the in this block diagram, I can directly write it as it's a sum of X cap and EQ, isn't it? So that is X cap of NTS plus EQ of NTS, isn't it? Right. Now let us substitute what is X cap of NTS. Okay, let's keep X cap as it is. Let me write like this. X cap of NTS, right? Plus, I'll substitute for EQ. Ah, okay, so that is E of NTS plus QE of NTS, isn't it? Okay, now write equation for E of NTS. X cap of NTS plus, what is the E? It is X of NTS minus X cap of NTS, right? Plus, not minus, it should be plus, okay? QE of, only for E I substituted, right? Now I can see that, so this and this will be cancelled. They are same. So X cap of NTS actually has nothing to do here. It gets cancelled ultimately. So quantized XQ of NTS is nothing but this is X of NTS, original sample, okay, input X of plus just the quantization error. This is what I require, I expected ultimately, correct? XE of NTS. So from this you actually predict what is X cap. That's all. Okay, fine. So these are the equations governing what we call as the DPCM encoder. Okay, now I have to perform what is called as a decoder. All right, DPCM decoder. So I have to perform each and every operation that resulted in DPCM, right? Whenever I converted whatever I did, I am supposed to do a reverse of that. So you see, last step is DPCM. Now I have a DPCM, I have to do a decoding, right? Because the last block was encoded, correct? So I start with the DPCM signal. Take the DPCM signal and pass it through the block which performs the inverse of encoding. So that has to be the decoding. Pass it through the decoding. So as soon as you right you come out of this, you get which signal? That is EQ, correct? Because the error was there, the error was encoded, correct? So I'll directly get the quantized error, EQ of NTS over there, right? To this, right, I previously I obtained this by subtraction of x cap of NTS, isn't it? Right? How did you get the you just have to add it, correct? So perfect. So this is the addition block, but both the signals coming to this will be added, right? So let's bring the addition that component later. Let me say what do I get when I add. So when I do the addition, I'm going to get the xq, right? Xq of NTS. This is what I'm going to get. This itself, anyway, I did the prediction, right? So we have done the prediction already by using the same signal, correct? So I'll what I'll do, I'll take this signal and I'll give it as input to this. Right. So there will be a prediction filter. Okay. So this itself will go yes. So this output will be X. Right. So this is what is there. I have XQ, right? This is actually the sampled signal. Okay. If you remember the how do we convert a sampled signal back into the original analog signal, right? So you have to use a reconstruction filter that is a simply a low pass filter. I can write LPF. So we use a low pass filter, pass through that. So the output of this will be the original. Okay, so that is about this. Now let's quickly go through the problem. Pretty simple problems. Okay, so they're not very difficult. Now, so let's see the sequence. So always here you get the samples. Okay, x of n will be given. In the sense x of NTS itself will be given. Samples values are like this, say 2.1, 2.2, 2.3, 2. No, I'll write 2.6, 2.7, 2.8. This is the given sequence. All right, I want you to convert this into the DPCM signal, and I want to convert back from the DPCM signal back to the original samples. Okay, so just pass this sample through the low pass filter, you get your original signal back. Okay, right. So again, we use a tabular method for the calculation purpose. Okay, so start with the x of n given. Then here we'll try to make a approximation. X cap of n is equal to x quantized n minus 1. Past one previous one. Then I'll write the error signal. Okay, this is E of n. Then I'll do the quantization EQ of n. Then we'll write the XQ of n. Okay, so I'll write the equation for XQ of n as well. So, okay, what is the error? Okay, what is error? Error is x of n minus x cap of n. So let me just write the equation below so that we can trace. Okay, it's simply quantize. Okay, you don't have to do this. I'll tell you what it is. Then xq of n is the x cap of n plus eq. Okay, so these are the equations we are going to use. It's a quantization. E of n is there. You quantize in the sense you make an approximation. I'll tell you. I'll come to that. Okay, so let's write the given samples here. So 2.1, 2.2, right, 2.8. So this first column is over. Always you in the second column, first value will be 0 because you see it is some previous value. I don't have any previous value. Okay, subtract, because the next column is simply 2.1 minus 0, 2.1. Okay, right. Now you see you have to do the quantization, right? So the quantization rule we apply is the normal. How do you convert a something like a fraction into the whole number? If it is less than 0.5, that will be lower value. more than 0.5 or more than that, next one. Okay, right. Now you do this. So x cap is 0, eq is 2, so next value is 2. I'm adding this plus this. Just see the equation, that's all. Okay, here we have. Okay, I got it. Now, right, the you see xq of n minus 1, n is this 2 will be coming over there. Okay, so simply bring the 2 down. So there is a 2 here. Now you do this. 2.2 minus 2. This will be 0 0.2. Okay. So 0 0.2 closer value is 0. Right. So 2 plus 0 is 2. Okay. Again the 2 comes down. 2 point. Okay. 0. Okay. Again 2. Okay. Next. Once again 2 comes down. Or this is 0 0.6. This is 1. So 3. 3 comes down. 3 minus this, right? 0 0.303. Next, once again 3 comes below. 0 0.20 and 3. So what you send is the error signal, right? Okay, so that means again it's not okay. First I'll write eq of n 2 0 0 1 0. Okay, this is what is the EQ. So output I'll write after doing the encoding. So for just to show the purpose of encoding, I'll convert them into 3-bit numbers, because if it is just 0 and 1, 1 bit is enough. So you can convert into right as you require. So 0 1 0 0 0 0 0 0 0 0 0 1 0 0 0. So this is your output. Very simple, very straightforward. Okay. Now, so very similarly, let's go to the decoding part as well. So I'll assume the same input. Okay. So you have the, this is your DPCM. Okay. Now, by obvious means, I have to receive a DPCM, and first I need to decoder, apply to decoder. When you apply the decoder, you get EQ of n, that is 200100. Okay. So first, our first column will be EQ of n. Okay. Then the next one is to get the approximated value. X cap of n is equal to xq of n minus 1, where the xq comes from the next column. Xq of n is equal to the x cap of n. See, I have to do addition. Previously I did the subtraction. Okay, so this is eq of n. Okay, so let's write what I received. I received 2 0 0 1 0 and another 0. Okay, so this is what I have received. Okay, here I'll write the decoder. It's fine. Initially starting with 0. So simply add 0 plus 2 is a 2. Okay, next this 2 comes here, 0 plus 2, 2 comes here, 0 plus 2, 2. Then this 2 comes here, 2 plus 1, 3. 3 comes here, 3 plus 0, 3. 3. So now you see, now here is, this is the point where we observe the effect of quantization and the error introduced because of the quantization. So this is the received, whenever I try to decode. Okay, decoded signal is this, that is 2 2 2 3 3 3. But if you recall, right, what was it transmitted? 2.1, 2.2, 2.3, 2.6, 2.7, 2.8. Correct? That's because of the, this is the error that comes here just because of the quantization, effect of the quantization. Okay. So anyway, right, we have sophisticated methods to, right, keep monitoring this, and right, if there is a huge error because of this, anyway, we can cancel that as well. Okay, but anyway, so the decoded version will never be exactly matching to what you have sent in case of DPCM. This is the point you have to remember when you solve. Okay, so that's all about the DPCM, its block diagram and the problems.